one thing to keep in mind, the second derivative is the derivative of the first derivative, where the first derivative is increasing, the second derivative is greater than 0, and where the first derivative is decreasing, the second derivative is less than 0. So notice that to the left of the y-axis here, where it's concave down, that first derivative is decreasing, which means that the second derivative is less than 0. And to the right of the y-axis, where it's concave up, that first derivative, those slopes, the tangents, are increasing. So the second derivative is greater than 0. So that leads us to yet another test in this section, concavity test, which now deals with the second derivative. So if the second derivative is positive on an interval, then the graph is concave up on that interval. And if the second derivative is less than 0 on an interval, then the graph's concave down there. And the point where it changes concavity is called an inflection point. So in this case, that critical value at the origin is also an inflection point. And that's where it changes from concave down to concave up. So here's another example. Find the local extrema of this function and find the intervals of concavity and the inflection point. To find the intervals of, start finding the local extrema, so we'll find the critical values, the critical numbers. So we find the first derivative and set it equal to 0. Solving this equation, I get critical numbers of pi over 2 and 3 pi over 2. Then using that first derivative test, we're going to test around each of these zeros. So testing the first derivative to the left of pi over 2 gives me a negative, and to the right of pi over 2 gives me a positive. So pi over 2 is a local minimum. To the left of 3 pi over 2, I get a positive derivative. And to the right of 3 pi over 2, I get a negative derivative. So that means that 3 pi over 2 is a local maximum. So now we're going to determine the concavity and the inflection points. So we'll find the second derivative, which is this equation. And to find the inflection points, which is where it changes concavity, we'd need to set this equal to 0. And solve. And so using a trig identity here to get everything in terms of sine, and then using the quadratic formula with sine x instead of x. And I find that the inflection points occur at where the sine x is 1/2 and -1. So this interval, remember, was 0 to 2 pi. So this happens when x is pi over 6, 5 pi over 6, and 3 pi over 2. So we have to test around pi over 6. So testing to the left of pi over 6, I'm testing the second derivative now because I want to see where it's concave up and concave down. Testing 0 to pi over 6, I use pi over 12, and evaluating the second derivative there, I get a value less than 0. So f is concave down because the second derivative is less than 0 on this interval. Now I'll test a point in the next interval between pi over 6 and 5 pi over 6. So I chose pi over 3, and that was greater than 0. Therefore, f is concave up between pi over 6 and 5 pi over 6. And then between 5 pi over 6 and 3 pi over 2, I choose pi, and the second derivative is less than 0 there, so it switches to concave down again. And then 3 pi over 2 to 2 pi, I chose 11 pi over 6, it's concave down there again. So let's look at this. So the blue graph is the second derivative. The red graph, the solid red graph, is the function itself. So I'm going to turn off the first derivative for a second. So notice that it's concave down where that second derivative is less than 0. And then that red graph is concave up where my second derivative is greater than 0 above the x-axis here. Now notice that this is going to be an inflection point because my second derivative is 0 and my graph is changing from concave up to concave down. Therefore, my second derivative is going from positive to negative. So that second derivative is negative. That blue dashed graph is below the x-axis all the way until we get to 2 pi. Now notice how this flattens out here for a lot longer than here. And that's because it's actually because the first derivative is also 0 there. It's called a stationary point then. So notice that at that inflection point, when I turn this green dashed graph is my first derivative. So I'm turned that back on in this picture. So notice that the place where it changes from concave up to concave down is an inflection point. And since that's a 0 of the second derivative, it's a max or min of the first derivative, since this is changing direction, changing sign. So another interpretation of an inflection point is that is where the function is changing the most rapidly. It has the most extreme rate of change there. Because remember, the first derivative is the rate of change of the function, and this is a maximum of the first derivative. So keep that in mind as another interpretation of inflection point.